motion. All right, so now we're going to look at angular momentum, okay? So let's talk about angular momentum. We talked a little bit about what momentum is. Of course, momentum is, and this is a short lesson, momentum, regular momentum, linear momentum. If you looked at linear momentum, which is P, is equal to mv. So if we take that and turn it into angular momentum, which is capital L, L is equal to the analog to the rotational analog to mass, which we learned last time was inertia, and the rotational analog to velocity, which is omega. So L equals I omega. The units, of course, for I is kilogram meters squared, and then this is radians per second. So we are going to end up with kilogram meters squared per second is our units. Okay. You can have an angular impulse. What is that? It's an outside torque. Outside of the system, right? That's applied for a short time, just like a linear impulse, okay? Angular impulse is equal to change in angular momentum, so delta L, just like J is equal to delta P for linear, J theta, which is how we distinguish it being angular, is delta L. Well, delta L is going to be equal to torque times time, okay? Just like this is equal to Ft for linear, then it becomes torque times tau times t, because torque is the force equivalent in rotational motion. So linear momentum, however, is ruled, if you notice, by both the angular momentum, by both the inertia and the angular velocity. So as I goes up, L goes up, or as our angular velocity goes up, angular momentum goes up. Now, if I is set, or if L is set, then as my inertia goes up, my angular speed goes down, or vice versa, okay? So let's look at how this is used, this idea. We have a uniform rod, 3 kilograms, 2 meters long, rotates about its center. That's giving us our pivot right here. So there's my pivot. By the hammer of Thor, love that, the rod is struck by a 1,500 Newton force for 0.08 seconds. So it's giving us a force and a 0.08 seconds. It's giving us a time, a short period of time, okay? That's directly perpendicular to rod. What's the angular velocity of the rod after impact? So we want the angular velocity of the rod after impact. So let's figure out what. We know we're going to have this because this is going to be equal to delta L, and we want to know the angular velocity. Well, we know the angular L is equal to I omega. So if we can find L, we can find I omega. So this is also equal to torque times the amount of time. That's going to be equal to L final minus L initial. Well, L initial, if it's starting from 0, is going to be 0. In other words, it's not rotating. Okay, so there's this. So what we have now is torque times time equals I omega final. So we can find the angular velocity. So let's start by finding the things we need to find. Torque, of course, is equal to Fr. Well, the force is 1,500. And R, if it's 2 meters long, but the center is here, the center, the distance from it is 1 meter. So this is times 1. So torque is equal to 1,500. Okay? So if the torque is equal to 1,500, then we need to know the time. So we have 1,500 times the time, which is 0.08, is equal to I. Well, let's find I. Rod about the center is 1/12. Mass is 3 kilograms times L. Well, L in this case is the length of the rod, which is 2 meters. So 2 squared. So we have 4 times 3, so I is 1. So this is 1 times omega final. Okay. Now, the only thing we need to figure out is the sign on the torque to make sure everything's okay. So if we strike with the hammer, it's going to be moving this way, which is clockwise, which means we need to throw on a negative onto this. So this is negative and this is negative. All right, because it's going clockwise anyway. So 1500 times 0.08. Is 120. So the final angular velocity is negative 120 radians per second. All right. Applying conservation of angular momentum. Guys, just like we have conservation of linear, so if we had linear, remember we said P initial equals P final? Well, conservation of angular momentum, we know that L is always conserved unless what? Unless an angular torque, external torque is acting on the system. So if there's no external torques, that means the sum of the torques is 0, right? That means there is conservation. So L initial equals L final. Internal torques don't change the angular momentum, only external torques do. They don't change the angular momentum, but they can change the energy. Okay? So this is important. As long as you fulfill here. Unless you have external torques acting, then L initial equals L final. Just like we said, no external forces acting meant we had a conservation of momentum. So no external torques, we have conservation of angular momentum. So let's look at a couple of examples here, and we'll be done. Baggage carousel has a mass of 500 kilograms and is in the shape of a disc with a radius of 2 meters. Okay, so if we've got a disc, what they're telling us here, shape of a disc, disc has an inertia of mr squared, okay? Oh, disc, 1/2 mr squared, excuse me. All right, no torques acting, no external torques acting on the carousel. So we immediately know L initial equals L final. We should always write that down when we see that. All right. So we're going to drop a piece of luggage or 10 pieces of luggage onto the carousel, find the speed of the carousel after they're acted. So if we have no external torque acted on it, then what's going to happen? We're adding mass, which means the inertia is going up. So adding mass, inertia is going to go up, which means angular velocity goes down. So we're going to expect the angular velocity to decrease. In other words, it's going to slow down its rotation. Okay? So the first thing we need to do is figure out what I is for the total thing, okay? So inertia total is going to be the inertia of the carousel plus the inertia of the luggage. Luggage is a point mass. So the inertia of the luggage, inertia for a point mass is just mr squared. So there are 10 of those. So let's figure out inertia for the carousel is going to be the mass of the carousel, 500 times the radius of the carousel, 2 squared divided by 2 plus 10 pieces of luggage each of which has 20 kilogram mass, and they're dropped onto the carousel. Well, they're going to be dropped onto what carousel? They'll be dropped at the edge, won't they? Isn't that usually where you put them? So we're going to say this is also 2 if we put them right out at the edge, how far they are from the center. So when we work this out, what do we get? So we get 1,800 kilogram meter squared. Okay, so there's my I for total for the whole thing. All right. So what we need to figure out is L initial is going to be I initial omega initial, and this is going to be I final omega final. Well, I initial is just going to be the carousel moving. So that's just going to be, this is just going to be this, which is just going to be this, isn't it? So we've got 1,000 on the one side times omega initial. It's going 1 radian per second, so times 1 is equal to I final, which we found was 1,800 times omega final. Okay, so 1,000 divided by 1,800. So 0.56 radians per second. So that was pretty easy to find. All right, so the last thing we need to look at today is what is the angular momentum of a particle? In other words, if you are sitting still and someone goes running by you, believe it or not, they actually have angular momentum with you. Even though they're not turning, the fact that they're going by you gives you angular momentum influence over them. It's minuscule and you don't notice it, but it does happen. It's the reason why, that's the whole reason why things continue to orbit in space, is every place in space, like the sun, the Earth is passing by the sun, so it applies angular momentum to it. As a matter of fact, the angular momentum is the radius as it gets closer to the sun, since it's not in a circle. If you think about it, and you have the sun right here, and a planet, let's say Jupiter. Over the same amount of time, Jupiter's going to sweep from here to here. It's got angular momentum, and then as it gets closer, it's going to move faster, so it's going to sweep out wider. What you're going to find is that the area of both of these represents the angular momentum. This will be L closer, this will be L further away, and those are the same. It sweeps the same amount in the same amount of time. It's just going to be going faster as it's closer, because as the radius from the sun, as the distance from the sun decreases, the angular momentum increases, and therefore the speed increases. Further away it is, the higher the inertia is, the speed decreases. So you've got this inertia going up, speed going down, or inertia going down, speed going up, okay? As r is the distance from the sun in the orbit goes, continues through. Now, what we find is, how can we find the linear angular momentum of some particular point mass? Say you're here, and an object passes by you, mass m, going this way with some velocity. How do we figure that out? Some distance away from you, we have a formula, L equals mvr. And that is the last formula that you're going to need to know in this section, okay? mvr. All right? So let's use that. So even if it's moving through space linearly, it can still have angular momentum. Now, Angular momentum and linear momentum are both conserved individually. So maybe you ought to write that down. And that's in a collision or not in a collision, okay? They are conserved separately or independently. So you can treat them separately or independently. Just know they're both there. All right, so let's look at this. We've got a bullet, mass 0.2 kilograms, shot at a 40 kilogram door at its unhinged end. So we've got a door here on a hinge. We shoot a bullet at it. Bullet's being shot at its unhinged end. There's our bullet flying towards our door. And it's initially going 200 meters per second and travels perpendicular to the plane door. So it's going to hit the door, and you know what's going to happen. The door is going to swing shut, isn't it? Or if it's shut, swing open. All right, so it says, what's the angular velocity of the door after the bullet strikes? Well, it gives you this. This is treated door rod hinge, gives you the formula for I. So first thing we're going to do is say, all right, so before the collision, what do we have going on? We know this. L initial equals L final. All right? So L initial is just the bullet moving, correct? So it's going to be I omega for the bullet. Omega for the bullet. Final, it's going to be swinging together. It's going to be I for the bullet plus I for the door times omega final. And omega final is what we're looking for. So I for the bullet is going to be a point. The bullet is a point, right? So I for the bullet, if it's a point mass, is going to be mr squared. I don't want to even have to do that, though. Do you? Do we have an easier way to do this? What do we know about L? We just found it. We know the velocity of the bullet, don't we? So let's use our alternative formula we just found here, which is what? mvr. Since we know linear velocity, mvr instead. So we know that. We know the mass of the bullet is 0.2. Velocity of the bullet was 200. And it is... if it's 1.5 meters wide, that means that is its radius from the hinge, so 1.5. That's equal to I for the bullet, which is mvr plus what? Or mr squared, since we're doing it this way, mr squared plus 1/3 ml squared times omega final. So let's figure out what that is. Mass of the bullet is 0.2. Radius of the bullet, of course, is 1.5 squared. 1/3 mass of the door is 40 times what? Length of the door, same thing, okay, which is 1.5 squared. Because we're looking at the distance, the length this way. We don't care about how tall it is. We're just looking for this is our L. All right? So, times omega final. So let's figure out what we got here. So we've got 60 equals .45 omega final. So omega final is going to be equal to 60 divided by 30.45, which is 1.97. So 1.97 radians per second. So that's my final. All right, so here's your question. How would the answer change if the bullet hit closer to the door? If it hit closer to the door, hinge, I think is what they mean. Close to the door hinge, instead of at the very edge, closer to the door hinge. That means R would go down. So inertia would go down, right? So if there's inertia goes down, then angular velocity would go up. So the angular velocity would go up. So if the angular velocity goes up, the door swings faster. Okay? Take your notes and do your homework, all right?